chapter 17, we are going to start getting into harder stuff now. We're going to be getting into still titrations, and this is going to be weak versus strong. And so that's going to be what's making it hard, the fact that there's something weak in there. The strongs are the easiest ones to do, and I will just be quite frank that sometimes we get so hung up on how to do these hard ones, we forget how to do the easy ones. So before the test, before the quiz, you want to make sure you look back over a strong, make sure you remember how to do the strong. So we're going to be talking about weak versus strong. There's two types where you could have a weak acid, and you could be titrating it with a strong base, or you could have a weak base and titrating it with a strong acid. We're going to be picking up with letter C on your worksheet, so letter C, and that is going to be a weak acid with a strong base. So we're going to be doing a weak acid. In our flask in the beginning, we've got 25 milliliters of a 0.1 molar sample of lactic acid. So that's going to be in our flask in the beginning. And we're going to slowly add in some sodium hydroxide. So we're going to add in a strong base. Okay, we've got several points on our graph to go over. The very first point is 0 milliliters of the base added. So 0 milliliters, let's do milliliters of base. And we want to know what the pH would be. Well, if there's no base in there, then you wouldn't write a reaction with the base. There's 0 base in the reaction, so you would not write a reaction of your acid plus your base. So how do you find your pH of a weak acid? Well, they gave us a Ka. The Ka is 1.38 times 10 to the negative 4th. Now, if it were a strong, I would just take the negative log of 0.1, and then the pH would be 1. So strongs are very, very easy to do. This one's a weak. So how do you find the pH of a weak acid if there's nothing else in there? Well, this is where we're going to do a RICE equation. At the 0 mark on a weak, we're going to do a RICE equation. And so we simply do a RICE by breaking down our acid. You could put it plus the hydronium if you want, or you simply could break it down. So you've got a 0.1, this is 0, 0, minus x, x, x. So just a very simple RICE equation for the 0 mark. Again, for strongs we don't have to do that because they break apart 100%. So very simple. We could use our solver or not use our solver, whichever you prefer. Okay. And then our x on this one, let's see if I can put it down somewhere. But anyway, you could solve this one. This one's not anything that you couldn't solve. And then to find pH, since this is an acid, we are using Ka, so we just simply take the negative log 0.00365 to find our pH. So our pH here will be 2.43. So at the 0 mark, you're just simply doing just a real basic RICE equation. Alright, so that was our 0 milliliters added. So now we're going to slowly start adding in some base. So we're going to do the next point, which is the 4 milliliters of base being added. So I'm going to come over here. Let's get our reaction. We're going to have 25 milliliters of 0.1 molar lactic acid. And we're going to be adding 4 milliliters of 0.1 molar sodium hydroxide. Alright, so now we're going to get an acid-base reacting together because there is some base there. So we're going to write our equation. Doesn't matter who you start with. Just a double displacement reaction. This is going to be a 1 arrow. Don't know why I wrote him up so high there. one arrow going on. So you're going to make sodium lactate, and you're going to make water. So if we do the net onyx, and I do highly recommend net onyx, then this will be breaking down, this will be boxing as a weak acid, this will break apart, and of course this is water. So our spectator here is the sodium. Alright, this is an acid-base reaction, so we're going to do a RICA. Alright, so now we're going to go 2 moles. And this will be 0.0025 moles. Nope, put the wrong one. So sorry. My base here is 0.0004. Remember, moles, molarity times liters there is going to get us moles. And this guy is 0.000. We're starting out at 0 here. We don't really care about the water. It does start out as 0. This is not just a spectator this time on this problem. Again, making the smallest one go away, so very similar to what we did before. So if I subtract that, then this is what gets added over here. I'm going to lose a 0. I feel like I added a 0 somewhere. My goodness, how many zeros I got going on in there? One too many, I think. Going a little 0 happy here. Alright, 3 zeros. That up there should only have 2 zeros. There's and lies my problem. Okay, I think I'm good now. 100. I taped this earlier and I accidentally pressed the wrong button and deleted it, so I'm having to tape this again. So I'm kind of hurrying and not doing a great job here. Okay, I think I have the right amount of zeros going on. 0.004 times 0.1 should give us 3 zeros. 0.025 times that should. So this is my moles of each. Make the smallest one go away. This is, and we add on the other side. So now we should be good. Okay, so now, unlike the strong where you have extra stuff left over, either OH or H+, and then you can change it back to molarity and then simply find the pH, we don't have extra OH. My OH is gone in this case. So that's my limited reactant. So what you do have left is a weak acid and a salt. So if you can recognize that, you could then use Henderson-Hasselbalch. So Henderson-Hasselbalch is pH equals the negative log of the Ka, and it's always the Ka. Doesn't matter if you're dealing with an acid or a base, Henderson-Hasselbalch requires you use that, plus the log of the base, which in this case is up here, divided by the acid. Now, I want to point out something, and a lot of people are missing it on the quiz, is when you use the Henderson-Hasselbalch, you can leave it in moles, or maybe you should change it to molarity. I'm beginning to wonder if I should make everyone change it to molarity at the A, because people are forgetting to change it later. I thought I was being nice by letting you leave it in moles. This is a proportion, and the mole proportion and the molarity proportion are the same thing. But if you were to change it to molarity, you would need to divide by 29 milliliters. You would divide this by 0.029. This is divided by 0.29. The proportion here is going to be the same. So Henderson-Hasselbalch works in moles. The negative log does not work in moles, and some people are missing that on their quiz. Alright, so when I do this, you come out with a pH of 3.14. Alright, so I did a RICA, then there was actually a buffer situation going on, so I could use Henderson. So I did a RICA and a Henderson-Hasselbalch. So over here, this would be 3.14. Okay, so if you had to do the next point, you could do all those. They're all going to work the same, so not hard. We haven't reached anything hard yet. So I want to point out a special point. I would like you to put a star by it on your thing, and that is going to be the 12.5 mark. It's not always 12.5. In this particular reaction, it's 12.5 mark. So if it's 12.5, this is going to change on us. And I want to show you. Probably do better just erasing it all. It's easier for me to erase than to rewrite all this. Alright, at 12.5, you would have 0.00125 moles of NaOH. You would have subtract, that would be how much we would subtract. And that's how much would get added over here. So not looking hugely different, same thing going on, just my moles change. But here's what I wanted to point out. Your base would be 0.00, and here's your acid. What do you notice here? This is what we call the best buffering situation. The best buffering situation is when your weak acid and your salt are equal to one another. This is a special point. That's why I would like you to put a star by it in your thing. This is called midpoint. Midpoint is when the best buffering is going on, when you have equal moles of your acid and the weak acid and its salt, or the weak base and its salt. So this falls out of the equation, and you simply would not even need to do all this. If you can recognize, oh, that's midpoint, I could just take the negative log of the Ka, and you would simply find the pH of the solution there, just the negative log of the Ka, and you would get 3.86. So back to our chart, you're going to fill in the rest, but 12.5 here, putting a star by it because it's called midpoint, and it was, I lost it, 3.86. That's where the best buffering is going on at that point there. Alright, so what we did so far, we did a rice at 0. Up to this point, we did a RICA, and you could do Henderson-Hasselbalch. I'm just going to put HH. At this point, I'm out of room here, you could just take the negative log of the Ka. You really wouldn't have to do anything at midpoint other than the negative log, and that is plenty of work to show for midpoint. After midpoint, you could still do the RICA, and you could still do Henderson-Hasselbalch, because there's still going to be buffering. Buffering is going to take place all the way up to midpoint and after midpoint until we get to a very special point called equivalence point. In this particular one, it's the 25 milliliters. And what do you notice about this and that? Well, the midpoint is halfway to equivalence point. So if you know the equivalence point, it's half the amount is midpoint. So that's if the equivalence point was 30, midpoint would be 15. If equivalence point was 40, midpoint would be 20 milliliters. And you could just take the negative log of that. This is going to be the mean guy here at equivalence point. So let me go over here, back to our equation. You might want to write your equation again. In this particular problem, the way our equivalence point is 25 milliliters. The way we would find this if we didn't know it is we would use the formula MV equals MV. This would be your acid, this would be your base. What we're saying is moles would be equal. So the molarity times the volume of your base would equal the molarity times the volume of your acid. This one's really easy because these numbers are the same. So the same molarity would have the same volume at which they would be equal moles. So we're going to do 25-25 for this particular problem. So do you notice they're equal moles? So if we made the smallest one go away, do some erasing here. At equivalence point, you no longer can use Henderson-Hasselbalch. Get him out of there. And here's the reason why. Smallest number is the same on both sides. So they both go away. So if we add it over on this side, unlike strong, where this is a spectator or a neutral salt, this right here is a basic salt. If it's strong, equivalence point, the pH is 7. You don't really have to do any work. Equivalence point, pH of strong is 7. This one is not 7 because it is not a strong, it's a weak strong. And this guy is what's causing the problem. This is a basic salt that will do something in the water called hydrolysis. And so this is going to be where dirty rice comes in. This is the hard part. So you're going to do a RICA. Your acid, your base go away, you make salt. You're then now going to change it back to molarity. And you're going to divide by the total volume, which is 25 and 25, which is 0.05 liters. And then you're going to take your equation, you're going to flip it around. And you're going to do a rice. And we're going to still get rid of our spectators so we can see something. Okay, so if we will flip this around, what we will find that this is 0.05. Molarity now, because it's a rice table, this will be 0, 0. Because it's rice, our small number doesn't go away this time, so we're actually going to end up with some values. So now we will have minus x, 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 0.05 minus x, then with x squared over 0.05 minus x equals. Now we've got to decide Ka or Kb. Do you see this right here? That's a basic salt, it's Kb. And I will just be quite frank, it's always opposite what they give us in the problem. They gave us a Ka, 1.38 times 10 to the negative 4th. We don't need Ka, we need Kb. So we will need to find Kb. And the way you find Kb is by taking 1 times 10 to the negative 14th and dividing by our Ka. Come out with 7.25 times 10 to the negative 11th power. And then you can solve for your x, which is 1.9 times 10 to the negative 6. If we trace the x back up into our table, that's our hydroxide concentration there. OH. That's why we want to do the net ionics, where we can see OH or H plus staring at us. So we can find the POH by taking the negative log of that value, and you will find the POH is 5.72, and so our pH is 8.28. Okay, let's look what we did. This is called equivalence point. Ugliest point. Equivalence point where you have equal moles of acid and base. First thing is your moles of your acid and base will equal one another. You will do a RICA. You will get your amount of your salt. You will then change your moles to molarity. So divide by the total liters. This is total here. Then you'll flip your equation around and you will rice it. And you will use not the Ka or Kb if they give you, you'll use the opposite. If you'll do the net onics, you will see it. And then you'll just plug back into the equation like we've been doing. So this is known as a RICA rice, or students call it a dirty rice. Students in the past called this a RICA, change-a, flip-a, rice-a equation. So if you want to call it that, you can call it that. So 8.28 is our value here. So 8.28. So this is where, at equivalence, where we had to do a RICA. You had to change to molarity. You had to flip the equation. And then you had to rice. And when you rice, you change your K value. So it's the ugliest thing. Here, RICA, change to molarity, flip the equation, rice it with changing the K. and then you'll just take negative log with whatever you've got. So it's the ugliest point that you've got. Alright, let's do just a little bit past. Let's do the next one. Let's do 25.1. Not very much past equivalence point, but it's past equivalence point. And what this will change is we'll change this guy. There's 25.1. So smallest number will go away, but now we're going to actually be left with some extra OH. There's going to be the problem child there. Not really the problem child. It's actually going to be a good thing for you. I will tell you can RICA RICE all of these if you prefer. If you don't want to learn any of the shortcuts, you can do RICA RICE for every single one of these equations. One year I did have a student that preferred to do that because they just thought it was easier than figuring out all the different things to do at each step. But if you'll look at what you've got in the equation, what's left, it kind of makes sense after you work a few of them. Alright, what's left? You've got a base, strong base, and not even his conjugate salt. It's the conjugate salt of this thing. So you cannot use Henderson-Hasselbalch after equivalence point. I will tell you could change both of these to molarity. You could flip them around. You could rice them. But what we're going to find is that this guy really does not have much effect. It is a basic salt, but it does not affect the base very much. Where we're going to get our pH is right here from this hydroxide. So if there's extra OH or H+, you can just use the equation. In this case, POH is the negative log of OH minus. Here's the problem, and a lot of students have missed it. Anytime you use this equation, this must be in molarity. If you use this equation, it must be in molarity. If you leave it in moles, it will not work. That is moles. So I have to take the negative log of 0.00001 moles divided by the total volume. The total volume in this case, I had 25 milliliters and I had 25.1 milliliters, which is a total of 50.1 milliliters, which would be 0.0501 liters. If you do that, you get a POH. Let's see where I broke this one out. Of 3.7. And so your pH is 10.3. So back to my chart. This was the 25.1 mark. You'll get a pH of 10.3. So what we should see going on, let me pull up this little thing here. Do this way with it. We should see it starting out low, then it goes up, and then it peters out again. So this is the way our graph should look, something like this. Here's some important parts on our graph. You have the 0 mark. At 0, you do a simple rice if it's weak. If it's strong, you just take the negative log of it. At midpoint, which is halfway, you could just take the negative log of the Ka to find the pH. This is equivalence point. Notice that there's, in this region, there's the same amount of distance here and here. So your graph should kind of look like this. Same amount of distance here and here. This is where you do the dirty rice. I'm just going to put dirty rice. That's where the RICA, change-a, flip-a, RICA comes in. It's the ugly stuff here. After equivalence point, all this up here, you're going to have, in this case, extra base. So you're just going to do simply a RICA equation. You're going to change it, change to molarity, and then you're going to take the negative log of whatever you got. In this case, it's extra OH, and then you'll need to find the POH. All this region going on in here, before we get to that equivalence point, you're going to take a RICA, and you can do Henderson-Hasselbalch. And the reason you can is that's when buffering is going on. You got the best buffering going on before equivalence point. So you can use RICA and then Henderson-Hasselbalch. And that's pretty much the way a titration curve will look. Best buffering going on here. Let's talk just a moment about indicators, and then we'll talk about the letter D problem. When you're choosing an indicator, let me go back to the PowerPoint, you want an indicator that's going to be closest to your equivalence point. But the best indicator, well, your best indicator is going to be the one closest almost exactly to your equivalence point. But you want your indicator to at least change colors in this region. So if I were choosing an indicator for this particular reaction, I'd want something that would change colors about 6.5 or 11, or anywhere in between there. I'd want it to change colors. I wouldn't want it to change colors up here. I wouldn't want it to change colors down there. So let's look at, so I said 11 and 5.5 in this one. So here's a list of indicators. So I'd want something from here to here. So, whoa, I can't draw straight. So any of those indicators that are in that region would be the best. And the best would be the one that was closest to the equivalence point, which was right around in here. So this thymol blue would be the best one for the one we just did. Okay, so again, the best indicator is the one that is closest to your equivalence point. On your test, I'll give you a list of indicators. You'll choose which one's the best for the titration that you're doing. Here's one where it should be a strong, where the pH is 7. A good indicator for that would be phenolphthalein, even though it doesn't change at 7, or methyl orange, because it's in that range. We actually don't have an indicator that changes at 7 itself. So that it will explain indicators. Very easy to do for indicators. So let me X out of that. That's pre-AP. And back to this. Alright, so we went over all the points. At 0, you're doing a RICE. Before equivalence point, you can do RICA, and you can do Henderson-Hasselbalch. There's a point right there called the midpoint. You could just do the negative log of the Ka. This one is the RICA, change to polarity, flip, and RICE by also changing your K. And then after your equivalence point, you can simply do a RICA. You still got to change back to molarity, and you got to take the negative log. You'll either have extra H plus or OH, and so you may have to subtract from 14. So letter D has you using a weak base, which is ammonia, and you're slowly adding in hydrochloric acid. So let me help you at least set up the equations for this. At the 0 milliliters, you'll have nothing but ammonia in there. So you're going to do a RICE, and the way you RICE ammonia is you always put it plus water, and RICE has 2 arrows. It makes ammonium hydroxide, so it looks like this. So that will help you see the OH. So this is a base, so you'll use Kb for this problem. Alright, then you have to decide on some points. In order to find your equivalence point, you're going to use the equation Mv equals Mv, acid and base, and you could find the volume at which. So I would like you to graph equivalence point. And that's where you're going to have to do the ugly stuff. Once you know your equivalence point volume, you can half that, and I would like you also to do midpoint. So whatever your equivalence point is, half it, and that will be midpoint. Then I would like you to do some random point in between here. So I would suggest a nice even number. So once you know this value, you'll know either a point in here and a point in there. And then I would like you to do any point after equivalence point you can pick. So I'd like at least 6 points on your graph for letter D. So 0 is one of them. Let me put it in red. 0 is 1, midpoint's 1, equivalence point's 1, after equivalence point, and 1 point in between. I don't care either up there or down there, but after, in between 0 and equivalence point, but not midpoint, so I want that one to be included. So 5 points total for that one. Let me help you write the formula when you start adding the acid in there, because it's weird too. When you take ammonia and you put it plus hydrochloric acid, 1 arrow for your RICA equation, it actually makes ammonium chloride. Kind of weird. It's not a double displacement. You don't see water being formed. Water's there, it's just over here and over there. If we did our spectators, this guy would slash, and you will find that that chloride is what's spectating in this reaction. So here's your equation. I would recommend that you be able to write ammonia in water, so your 0 mark for rice, and be able to do an ammonia plus hydrochloric acid reaction. That's really going to show up on your test. Alright, hopefully this helped. I've done it twice now, so hopefully I didn't make a mistake. If you need to watch it again, watch it again. If you need help, please come in and see me.